Right now, the single greatest bottleneck to the future of artificial intelligence isn't, a lack of computing power,
Right.
isn't a shortage of training data, and it's definitely not the software. It's actually, well, it's a few inches of copper wire that is getting dangerously hot.
Dangerously hot is putting it mildly.
Yeah. Welcome to the deep dive. We are so glad you're here with us today. We're looking at this massive stack of incredibly dense financial notes, tech forecasts, and some really intricate market analysis graphics.
Yeah, and these documents, they map out this huge hidden physical roadblock to the entire global AI boom.
Right. And more importantly, they detail this multi-billion-dollar architectural shift that is happening right now to solve that roadblock. So, okay, let's unpack this because we are talking about what the sources are calling the next optical supercycle.
Yeah, it's a really striking phrase, isn't it? Optical supercycle. I mean, it sounds like something straight out of a theoretical physics paper.
It really does.
But it's actually deeply rooted in the physical, messy limitations of the hardware that runs, well, our entire modern world. So to understand the explosive market growth these sources are predicting for now, we have to start by examining the physical wall that the tech sector is just slamming into right now.
Yeah, let's talk about that wall because the notes are highly specific here. As these massive AI clusters try to scale up, they're hitting just astronomical data rates. The sources specifically mention 3.2 key data rates.
Right, which is massive.
Yeah, just to clarify for everyone, that is 3.2 terabits per second. And at those speeds, traditional copper wiring is being pushed to its absolute breaking point.
It's literally maxing out.
Yeah. The sources state that right now, these things called pluggable transceivers are the dominant solution in what they call scale-out architectures. But their energy efficiency is just falling incredibly far behind.
Well, yeah, because for decades, copper has been the undisputed king of data transmission inside these computing clusters. I mean, the premise is simple, right?
Sure, you just send an electrical signal down a copper wire.
Exactly. Data moves from point A to point B. And pluggable transceivers have been the workhorses doing that job. They take an electrical signal, push it through a copper trace on a circuit board, and you literally plug them in wherever you need them across these sprawling data centers.
Right, and in previous generations, when we were dealing with slower speeds, copper handled that perfectly fine.
It did, yeah.
But pushing 3.2 terabits per second through copper, I mean, I was trying to wrap my head around the physics of this. It feels like trying to shove a fire hose volume of water through a standard garden hose.
Oh, that's a great way to look at it.
Right, because eventually the pressure is just too much, energy gets completely wasted, and the whole system just hits a wall. That friction, that pressure, is essentially what copper does to data at these extreme speeds, right?
What's fascinating here is how accurate that analogy is, even down at the subatomic level. When you push that much data through copper, you are forcing electrons to alternate at incredibly high frequencies. And because of something called electrical impedance, those electrons actually start crowding to the very surface of the copper wire, which drastically increases the resistance.
Wow, just trying to force their way through.
Right, and that resistance generates heat. A massive system-threatening amount of heat. You also experience severe signal degradation. So the pluggable transceivers, they have to draw more and more power just to push the signal through the resistance of the copper over those short distances.
Wait, hold on, though. Whenever I see massive tech companies talking about a fundamental limit, I'm always a little skeptical.
Sure, I get that.
Is this just an issue of tech companies wanting to lower their astronomical electricity bills? Or is this an actual fundamental cap on how smart AI can actually get? Like, is this just an accounting issue?
No, it is a genuine, unbreakable physical wall. I mean, yes, power consumption is undeniably a massive headache for these companies.
Right. Cooling servers is expensive.
Very expensive. But if the energy efficiency of these pluggables continues to lag, and the sources explicitly state that it is lagging badly, AI clusters simply cannot scale.
Period.
Period. You reach a point where you literally cannot pump enough power into the building to cool the copper and push the data fast enough without melting the components.
Oh, wow. So the actual intelligence of the AI is bottlenecked by the metal wire.
Exactly. Its ability to learn and process parameters is strictly limited by the physical limitations of copper.
So if you literally cannot pump enough power into the building to cool these wires, you can't just build a thicker wire. You have to abandon electricity for data transfer entirely.
You do. You have to pivot.
Which explains this massive shift to light. Because copper is physically and energetically maxed out, A new standard just has to take over.
Sure.
And the sources declare a clear winner here. They call it the new star of architecture, which, is a pretty dramatic term for a dry tech forecast.
It is, yeah. But in the world of hardware architecture, an entire industry abandoning the fundamental element it's relied on for 50 years, that's about as dramatic as it gets.
Right, it's a huge deal. So the new star they are pointing to is CPO, or co-packaged optics.
The packaged optics, yes.
And the sources state that by adopting CPO, systems gain enhanced power efficiency and overall system resiliency. And this isn't just theoretical like whiteboard stuff either.
No, not at all.
Leading vendors, and the sources specifically name Nvidia and Broadcom here, have already begun adopting CPO in their switch products. They are commercializing it right now.
And the fact that Nvidia and Broadcom are driving this, that is the crucial tell for you. They're the absolute titans of AI hardware and networking infrastructure.
Right.
But to really grasp why they're making this shift, we need to look at what co-packaged optics actually physically does.
Oh, here's where it gets really interesting.
Yeah.
To picture what the CPO shift actually looks like for you guys listening, think about a traditional car. You have the engine under the front hood, right?
Right.
And it has to send power all the way down the drive shaft to the axles just to turn the wheels.
Exactly.
That physical distance means you lose energy along the way. That is the old pluggable copper model. The data has to travel across the circuit board.
Yes.
Co-packaged optics is like taking that car engine out from under the hood and integrating it directly into the axles themselves. By completely removing the distance the power has to travel, you just stop losing energy in the transmission.
That is a really perfect way to visualize it. I love that. In a traditional pluggable model, the optical transceiver sits at the edge of the circuit board.
Far away.
Right. The electrical signal has to travel across the copper traces on the board just to reach the main processor in the center. That distance is the drive shaft, where all the heat is generated and all the power is lost.
And CPO fixes that.
It does. Co-packaged optics literally packages the optical connection on the exact same substrate as the main silicon chip. You are moving the optical conversion process right next to the switch.
And the data is converted into light almost immediately.
Precisely. And this is why light beats copper. Photons, which carry the light, they do not suffer from electrical resistance.
Right.
They don't generate heat as they move through a medium, and they don't suffer from electromagnetic interference. By converting the data to light literally millimeters away from the processor, you are completely bypassing the copper bottleneck.
That is wild.
And when players of Nvidia and Broadcom's magnitude validate this architecture by putting it in their commercial designs, it forces the entire global ecosystem to adapt. They are essentially dictating the future physics of the internet.
But knowing that the big players are forcing this shift is really only half the story here. Because the sources detail exactly how this pivot to light is going to reorganize the landscape of the data centers themselves.
It's a huge framework shift.
Yeah, they introduce this critical distinction between scale-out and scale-up architectures.
And this distinction is vital for understanding the future of the market. The sources note that while pluggable transceivers dominate scale-out architectures today, the future of the CPO market is going to be primarily driven by scale-up applications.
Wait, so just to clarify, if scale-out is like building a massive sprawling city by adding more and more identical small houses like connecting thousands of standard servers over a wide area,
Right.
is scale-up like building an incredibly dense, ultra-efficient skyscraper,
Yeah.
just packing an unbelievable amount of compute power into one highly concentrated system?
Yes, exactly. Scale-out is simply adding more individual nodes to a network. Scale-up is making a single node phenomenally more powerful and tightly interconnected.
But the sources make a really aggressive prediction here. They say that aided by frameworks like OSI MSA, the scale-up CPO segment is projected to surpass scale-out applications before 2030
Yes, very soon.
and become the completely dominant market. Why does the skyscraper model completely take over the sprawling city model in just a few years?
If we connect this to the bigger picture, it really comes down to how artificial intelligence actually thinks.
Okay.
When you are training a massive large language model, the processors need to talk to each other constantly, instantly, with practically zero latency.
Right, they can't be waiting around.
Exactly. If one GPU has to wait for data to travel across a sprawling city of servers through traditional cables, the whole learning process just grinds to a halt. The AI cluster inherently requires the skyscraper approach.
Oh, I see.
It needs hundreds or thousands of chips, acting as if they are one giant cohesive brain. And to synchronize all those chips without delay, you need the massive immediate bandwidth that only light-only co-packaged optics can provide.
Can I see this OSI-MSA mentioned all over these blueprints as the catalyst for this? In software, we have open source standards to prevent walled gardens, to ensure different programs can talk to each other.
Sure.
Is this MSA framework essentially doing the same thing for hardware, like ensuring these different manufacturers can actually plug their optical parts into the same motherboard?
That is exactly what it does. MSA stands for multi-source agreement. In the hardware world, if every company builds its own proprietary CPO connections, like if Broadcom's lasers only work with Broadcom's chips...
Oh, right. And Nvidia's fibers only fit Nvidia's ports?
Exactly. If that happens, the entire ecosystem fragments. It becomes way too risky for data centers to upgrade because they get locked into a single vendor.
And nobody wants that.
No. So the OSI MSA acts as a shared universal standard. It guarantees interoperability. When everyone agrees on the exact physical specifications of how these light-based chips connect, it removes the risk for buyers.
Which accelerates the mass production.
Exactly. That shared standard is exactly why the sources are so confident about scale-up dominating by 2030.
Okay, so we have the technological superiority of light over copper, driven by the physics of heat.
Right.
We have the architectural framework shifting from sprawling scale-out to dense scale-up skyscrapers. And we have universal standards aligning the entire industry. Now we have to talk about the numbers.
Let's do it.
Because the financial and market implications detailed in these notes are just staggering.
Yeah, the projections in these documents certainly stand out from your typical hardware forecasts.
The sources project that the CPO market will grow by 142% CAGR compound annual growth rate from 2026 to 2030.
Which is massive.
The text literally describes this as almost parabolic growth over the next few years. They frame it as one of the best and earliest opportunities of this next optical supercycle. So what does this actually mean? Because in the financial world, a 142% compound annual growth rate isn't just growth.
No, not at all.
That means the market is more than doubling its size every single year. It is a rocket ship.
Yeah.
And the notes mention this 142% growth rate, excluding ELS, which I see stands for external laser source.
Right.
Why are they separating the laser source from the package in these growth projections?
Well, it comes back to the physics of heat again. Even though light doesn't generate heat as it travels, the lasers that actually create the light are highly sensitive to temperature. And the silicon chips they are attached to run incredibly hot, often approaching 100 degrees Celsius. If you embed the laser directly on that scorching hot silicon, the laser just degrades over time.
It just cooks it.
Basically, yeah. So a common architectural choice is the external laser source, or ELS. You keep the laser in a slightly cooler part of the rack and run a tiny microscopic fiber optic thread directly into the co-packaged chip.
Oh, I get it. So the financial analysts are just separating the core CPO switching market from the standalone laser market to give a more granular view of the revenue?
Exactly.
That makes total sense.
Yeah.
But I still have to challenge this parabolic chart.
Fair enough.
Are these numbers reflecting genuine physical hardware demand, or is this just more tech sector hype riding the coattails of the whole AI boom?
It is entirely fair to be skeptical of parabolic charts in the tech sector, especially when AI is involved. But let's anchor this back to what we discussed earlier, the garden hose analogy. AI models are not going to suddenly require less data. The models are only getting larger. The 3.2 terabit data rates are already here, and the next generation will be double that.
Wow.
Because copper is physically tapped out, moving to co-packaged optics is not a luxury upgrade. It's not optional. It is a mandatory infrastructure upgrade for the entire digital world.
Right, because you literally cannot run the AI systems of 2027 or 2028 on the copper pluggable architectures of today.
You can't. The chips will throttle or melt. So this 142% CAGR represents a frantic forced replacement cycle. The demand is literally hard-coded into the laws of physics.
It's a forced evolution for data centers.
Exactly.
And that leads us perfectly into the final piece of the puzzle here. If this optical supercycle is a forced upgrade, who is actually building the physical component?
Right, the boots on the ground.
Yeah, we've talked about the macro market view, but these notes also take us down to the micro level. They specifically name the specialized vanguard of companies stepping in to execute this massive transition.
And this is where the supply chain gets highly, highly specialized. We aren't just talking about Nvidia and Broadcom designing the overarching architecture anymore. We're talking about the granular manufacturing of light-based components.
The sources name a few key players taking on distinct roles here. They list Shunsin handling the packaging, MSS Core dealing with yields, and WinSemi acting as the foundry.
Right.
What do these companies actually do in this context? Because building a light-based chip sounds fundamentally different from stamping out a traditional copper circuit board.
Oh, it is a completely different discipline. Let's take packaging, which Shunsin is handling. In traditional copper packaging, you are essentially soldering metal contacts together.
Seems simple enough.
Yeah, but in co-packaged optics, you are trying to align a microscopic laser beam with a silicon waveguide that is a fraction of the width of a human hair. The sub-micron accuracy required is like trying to thread a needle from a mile away. It requires highly specialized robotics and incredibly sterile clean rooms.
And what about MSS Core dealing with yields? What does that mean?
So yield is simply the percentage of manufactured chips that actually work. In silicon photonics, because the tolerances are so impossibly tight, early manufacturing runs might have a yield of only 20 or 30%.
Wait, meaning 70% of what you build just goes in the trash.
Exactly, which makes the end product astronomically expensive. So companies like MSS Core, they specialize in process control and testing to push those yields up to 80 or 90%.
Yeah, so when you solve the yield problem, you drastically lower the cost per unit.
Right, which is what actually enables mass commercialization. And then you have companies like WinSemi, which operate the foundries, the actual fabrication plants that bake the silicon photonics wafers.
But the sources highlight one company in particular with a really fascinating advantage, and that's Sivers.
Sivers, yes.
They supply the lasers. And the text points out that Sivers has no material exposure to previous 800-gram pluggable optics, which makes them the bleeding edge leaders of CPO as laser suppliers.
Wait, 800 gram refers to the older 800 gigabit per second copper pluggables, right?
That is correct, the older, slower generation of copper technology.
It's like a company skipping the DVD era entirely and being born directly into the streaming era.
That's a great analogy.
Right. Because you would think having years of experience building the previous dominant tech would give a company an edge, maybe a war chest of capital or existing factory lines. But the sources are arguing that having zero experience with the old tech is actually their biggest strength.
This raises an important question about legacy baggage in the technology sector. Let's say you are a massive, established manufacturer of those 800 gigabit pluggable copper transceivers.
Okay.
You have thousands of employees, massive factories, and deeply entrenched supply chains, all dedicated to a technology that is currently hitting a physical wall. When the paradigm shifts to co-packaged optics, you face a massive internal conflict of interest. Oh, I see. You're cannibalizing your own revenue streams. You're trying to keep your old, profitable copper business alive while simultaneously trying to fund the R&D for the new light-based business.
Exactly. You are bogged down trying to salvage dying product lines, but a pure play company, someone like Sivers in the laser space, has zero legacy baggage.
Right.
They don't have to protect a dying copper-based revenue stream. They can dedicate 100% of their capital, their engineering talent, and their strategic focus strictly to the parabolic CPO curve.
Because they're building strictly for the light-based future.
Exactly. In a hardware transition, this rapid focus is absolutely everything. The companies that will define the supercycle are the ones entirely committed to the new architecture.
They get to ride that 142% rocket ship without any dead weight holding them back.
Precisely.
Okay, well, we have covered a massive amount of ground here today, and I just want to make sure we tie all these physical and financial threads together for everyone listening.
Sounds good.
We started by looking at the physical breaking point of the AI boom. 3.2 terabit data rates pushing traditional copper wires to their absolute limits, generating massive heat through electrical resistance and capping performance. Then we saw how co-packaged optics stepped in to bypass that friction entirely, moving the laser directly next to the chip to save energy and increase resiliency.
Which fundamentally changes how data centers are built, shifting from sprawling scale-out models to incredibly dense, light-driven scale-up skyscrapers.
And that architectural shift, backed by universal standards like OSI MSA, is triggering what the sources call an optical supercycle. It is driving a forced, mandatory 142% parabolic growth rate that is being executed by a specialized supply chain of legacy-free companies who only build for light.
It's an incredible transition. And as we wrap up, there is one final implication of all this that is really worth considering.
Yeah.
The notes explicitly state that CPO enhances overall system resiliency and bypasses the hard physical limits of copper. We are seeing the absolute pinnacle of our technology, Nvidia and Broadcom's most advanced AI switches, abandoning electricity for light just to survive and scale.
Because the physics demand it.
Right. But if you look at the world around you, we have spent the last century literally wrapping our entire planet, our cities, our streets, and the walls of our own homes in copper wire.
Yeah, everywhere.
Copper has been the nervous system of the modern age. But if light-based co-packaged architecture is proving to be the only way to achieve true efficiency and bypass the heat and resistance of metal at the very highest levels of computing, what does that mean for the rest of the world?
Wow.
How long until this architectural philosophy trickles down from the multi-billion-dollar data center and fundamentally changes the design of every single piece of everyday technology you own?
The ultimate trickle-down effect. From the AI skyscraper straight into your living room. A world entirely run on light. That is definitely something to think about the next time you plug a standard copper charging cable into the wall.